slides. Slide.
Who is online now?
You can start, so you cannot see them right now.
అసలు మీరు వ్యాఖ్యానం అన్నారు కొత్తది.
They're hearing the voice now. How can I know their response?
They will write.
Yeah.
People are doing it in the chat. You can see.
Hello, how many are able to hear me, please?
You can see.
How it will be if you come out with your names, please?
You can start with the session.
Okay. Now, I hope you remember one thing. Current electricity, what exactly it means? It is orderly flow of electrons, electric charges. It is possible to realize this electric current only in case of conductors with the movement of electrons, and in case of gases due to ions. In chemistry also you must have heard of anions and cations, and maybe the same type of electric current is realized with plasma also, where it is higher part of atmosphere, I was telling you. And in case of semiconductors, the electric current is a consequence of whole electron movement. But in our lesson purview, we are much interested in electric current flowing through metallic conductors. I hope you remember this much. If this is one metallic conductor, let us say that its length is L and its cross-sectional area is A. Now you made this point a one with higher potential, which I am calling as plus, the other one with lower potential as minus, and let us say the potential difference is V across these two ends. Once if the potential difference is V, the electric current was found to be flowing from positive to negative terminal. Let that electric current be I. I is the electric current flowing and V is the potential difference. I hope you remember at your high school level, the electric current and potential difference, they are related to one another. But how long this idea is correct? As long as the temperature and other physical conditions remain constant. So when temperature and other physical conditions remain constant, it was concluded by Simon Ohm, popularly known as Ohm's law, which you must have heard at high school levels. V is directly proportional to I. The current flowing through a conductor and potential difference across its ends are directly related. Then, to remove this proportionality symbol and to make this into an equation, we take the help of a constant of proportionality. That constant of proportionality happens to be capital R. So V is equal to, this is of course capital R. 1 minute. I want to make it. One minute, please. 1 minute. 1 minute. V is equal to R into I. Of course, here I failed to write, so forget about this. Here R happens to be the electrical resistance of the conductor. As you are seeing here, that electrical resistance R can be defined in this manner. Please look at that equation. R is equal to V by I. What is actually the meaning of V? It is potential difference. I is the electric current flowing through the conductor. So, electrical resistance of a conductor is the ratio of potential difference across the two ends of a conductor and the consequent current flowing through it, V by I. As you know, the numerator SI unit happens to be volt and the electric current SI unit happens to be ampere. So, volt per ampere happens to be the SI unit of the so-called electrical resistance. It was given a special name in the honor of scientist Ohm in SI system, that is Ohm. So symbolically we use this Greek alphabet, this one, omega. Actually this is capital omega. I hope you know the small omega written like this somewhere in rotatory motion, circular motion for angular velocity. But anyhow, now we are interested in this omega. So how we are going to define that electrical resistance Ohm? How you are going to put it in words, please? Ohm is the electrical resistance of a conductor which allows a current of 1 ampere when a potential difference of 1 volt is applied across its ends. I repeat, 1 ohm is the electric resistance of a conductor which allows a current of 1 ampere when a potential difference of 1 volt is allowed, 1 volt is maintained across its ends. But let us not forget one thing. This Ohm's law is not a universal law. It is not applicable all the time. Only when temperature and other physical conditions remaining constant, we are putting a class. When you study something about Boyle's law, we say temperature and quantity of matter remaining constant. Much the same way, temperature and other physical conditions remaining constant, this idea holds good. But I should tell you one more thing here. In case of metallic conductors, Ohm's law holds good, no doubt about it. But there were many cases where Ohm's law is not applicable. Can you go for imagining few examples, please? Can you tell me few cases where this Ohm's law is not applicable at all? The popular thing is, if you think about semiconductor devices, semiconductors, of course, luckily we have semiconductor electronics at a later level in the same academic year. But one thing is true, semiconductors are basically germanium and silicon making use of devices. There we talk about p-n diode, Zener diode. We are going to study those details. There, voltage and current are not at all directly related. These semiconductor devices which do not obey Ohm's law are known as non-ohmic conductors or non-ohmic resistors. Please remember, non-ohmic resistors are non-ohmic conductors. Not only semiconductor devices, later stage we go for talking about thermistors. In case of these thermistors also, Ohm's law is not at all applicable. Anyhow, let me talk to you something else now. Just now, we concluded with one formula, V is equal to R into I, where this R is known as electrical resistance of the material. Its SI unit is Ohm. Now the next question. When you are making use of one electrical conductor somewhere in electricity experiment, then we say that we are using that conductor as a part of electric circuit. I started using a new word, my dears. Please remember, electric circuit. What is an electric circuit? It is a closed path in which electric current flows. A closed path in which electric current flow is allowed, we go for calling it as a circuit. Now, I should tell you one more thing here. To indicate this electric resistance, I should give you a few examples like this. Say I have taken one conductor, number one. I have taken one conductor across which I maintained a potential difference of say 10 volt. And in that condition, I found that the electric current flowing through the conductor is 2.5 ampere. According to your formula, R is equal to V by I. When I make use of that, I go for writing this as 10 by 2.5. So, shall I conclude that the electrical resistance of the conductor under consideration is 4 ohm, please? 4 ohm. Now, let me give you one more example. There is one conductor across which a potential difference of 100 volt is maintained. 100 volt is maintained, and it was found that the electric current flowing in that particular condition is 10 ampere. According to your formula V by I, once again, the answer happens to be 100 by 10. It is coming to 10 ohm. So, electric resistance is not the same for all conductors, number one. And moreover, it was found that electric resistance of a conductor depends on the material under consideration and its physical dimensions. Material under consideration and dimensions. What are these dimensions? When you are thinking about a metallic wire, naturally some length of the wire comes to your mind. It will be having some cross-sectional area. So cross-section area and length, we go for treating them as the dimensions now. And obviously, when you are making use of Ohm's law for your study, temperature and other physical conditions are remaining unaltered. Then let me talk to you something else now. Please look at this. You need not have to write first, but first try to concentrate. By chance, if you are maintaining some book in front of you, whatever you feel like, simply the formula that appeared with the help of Ohm's law, V is equal to IR, is the first formula. And I'm sure you know this much. 1 minute. If I say that I'm making use of one formula like Y is equal to mx in mathematics, at high school level, it represents one straight line. Now, let me take this as the y-axis, this as the x-axis. Let me take voltage values on y-axis, the corresponding current values on x-axis. My dears, please observe, y is equal to mx. Just below that, I will write like this: V is equal to IR. I am writing it as RI. Then, once if you look at this, you'll catch one more point here. The minute I go for writing this as V is equal to R into I, if I go for comparing this with the Y is equal to mx, in the place of M, there is a letter R. On the y-axis, I have taken the values of V. On the x-axis, I have taken the value of I. In mathematics, people go for calling that M as slope. Slope is nothing but tan of the angle. Now for a conductor, if I draw the graph between V and I, as long as it is metallic conductor, of course, the straight line will be passing through origin. This is Y is equal to mx. So if you go for calling this particular angle as theta, and if you take tan of that angle, naturally the tan of that angle happens to be the electrical resistance R, please. So tan theta is equal to R. Please remember, this idea holds good only when you take V values on y-axis and I values on x-axis. But if somebody goes for representing voltage on x-axis, current on x-axis, my dear, please observe, I am reversing the coordinates. I values I am putting on y-axis, V values on x-axis. Then naturally R is given by the formula not tan theta but cot theta. So what it is worth, remember, when somebody says I am talking about slope of the line is giving resistance, obviously it means that that person is taking current values on x-axis and voltage values on y-axis. That's fine. Now, little bit more. Undoubtedly, the formula V by I helps you in calculating electrical resistance, no doubt. But let us say you are provided with a small piece of wire of copper, right? That copper wire is having some cross-sectional area. Then, when you are asked to calculate electrical resistance, then you say that I know the formula V by I. But as I was telling you 2 minutes ago, this V and I conditions appear only when you involve your conductor in an electric circuit. But without electric circuit, can't we not calculate electric resistance? Yes, it was found that the electric resistance of a conductor is directly proportional to its length. Use your common sense, please. When I say resistance is directly proportional length, I am saying that if I take a conductor of more length, its electrical resistance will be more. And moreover, it was found that resistance is inversely proportional to cross-sectional area. What does it mean? As the cross-section area becomes more, the resistance becomes less. Once if you combine these two ideas, in a single relation you can write like this: R directly proportional L by A. This happens to be one single relation between electrical resistance, length and cross-sectional area. Of course, please remember in your heart of hearts, we are much worried about the electrical resistance of a metallic conductor, that's all. Then the resistance is equal to what? When I want to convert this into an equation, I should take the help of a proportionality constant. That proportionality constant is rho. It is rho L by A. Please remember, rho L by A is the formula for electric resistance, where L is the length of the conductor, A is the cross-sectional area, rho is known as specific resistance. I write here, probably by understanding it may be good if you to start noting on your paper. It is specific resistance. That specific resistance has at another name resistivity. Specific resistance is also known as resistivity, please. These are synonyms either way. Then one more thing. The minute I say specific resistance and resistivity are same, they depend on the material properties. Copper resistivity is something, Brass resistivity is something, iron has some other resistivity. So every material in the periodic table has got its own resistivity. Please remember that rho is something talking about property of the material chosen for your purpose. Then I want to tell you something else now. Look at that. Shall I go for writing that rho in this manner? Rho is equal to R A by L. Just by cross multiplication method, I am writing this conclusion, please. The minute I write like this, the numerator R, SI unit is ohm. Area, SI unit is meter square. The denominator length unit is meter. So by cancelling this 1 meter, shall I end up with the answer that rho ohm meter is the SI unit for specific resistance rho, please? So remember, resistivity, specific resistance SI unit is ohm meter. Don't forget, it is ohm meter. Then let us go for looking at one more idea. If somebody says the resistivity is more for a material, what do you mean by that? It is not able to conduct the electric current through it easily. Then with your common sense, you can understand one more thing. Let us go for comparing the situation with the things going on the road. At times while traveling on the road, you feel that today the resistance of the road is too large for my pedaling of bicycle. The reason is probably that road is flooded with the traffic. If more number of people and other vehicles are there on the road, you feel that resistance is more. Much the same way, when a particular material has large group of molecules packed very closely, when molecular packing is more, obviously you feel that electrical resistance is more. Instead of you traveling through 1 kilometer road, if you are made to travel through a road of length 2 kilometer, means I am talking about doubling the length of the conductor, please. When conductor length becomes double, the resistance also becomes double. So what does it mean? The length of the road and the resistance offered by the road are directly related. Much the same way, please try to link up that with the physical thing happening. When electrons are traveling through a material, the difficulty experienced by electrons while traveling through the material is nothing but electric resistance. So instead of taking certain length of the conductor, if you take double the length of the conductor, electric resistance gets doubled. If you take triple length, it gets tripled. So that is why we are simply concluding that resistance is directly proportional to length. And please think about one more situation. When you say that a conductor is made up of atoms, each atom you think it as a ball. You have taken one box, you filled that box with so many balls. Even though you say that the whole box is full with balls, let us not forget one thing. In between the balls, there is small gap. In chemistry, we go for calling it as interatomic spacing. Because of that small size of the interatomic spacing, people go for measuring it in the units of angstrom units also. I hope you know this much. 1 angstrom unit corresponds to 10 power minus 10 meter. So when small gaps are there, electrons with some difficulty, they are traveling through small gaps, they are experiencing some resistance, very good. But if you take still thin material, you are making material thin, please. Think that so many small balls are taken in that rod, then material balls are very small. The interatomic spacing left between balls is also very small. That is why a thin wire, please remember, thin wire offers more resistance to the electron flow compared to a thick wire. In case of a thin wire, after all, you might have seen the filament made up of tungsten used in our incandescent electric bulb. In case of a bulb, the filament material, if you can see carefully, you feel it to be very, very thin. When material is very, very thin, when cross-section area is very, very small, obviously the difficulty experienced by electrons will be more. When electrons experience more difficulty, they lose more energy. The energy lost by more electrons appears in the form of heat energy and light energy. That is why a thin wire with more resistance glows more brightly when electric current is flowing through it. But once if you say you have taken a thick wire as thick as myself, then if the material is very thick, interatomic spacings are very large, then happily electrons can travel with the least difficulty. That is why people say electrical resistance is more for a thin material, it is very less for a thick material. The minute you say electrical resistance is less for a material, indirectly you are saying that conductivity is more. Obvious, na? When resistance is less, conductivity is more. Or when resistance is very very much, resistance is very high, that is for a thin wire, you are saying that electrical conductance is very low. So whenever resistance increases, conductivity decreases. That is why people started saying electrical resistivity, conductivity are inversely related. Just now I have written here, the value of rho, calling this as electrical resistance, specific resistance or resistivity. The reciprocal of resistivity 1 by rho is given a special name in physics. We call it as conductivity sigma. Please remember, 1 by rho, reciprocal of resistivity is conductivity. The minute you say the SI unit of rho is ohm meter, what should be the SI unit of this sigma, please? It should be ohm inverse, meter inverse. And I should tell you one more thing. Simply R we call as electrical resistance. Na? The reciprocal of electrical resistance 1 by R is known as conductance. It is conductance. Its symbol is S. And of course, people use one more symbol for that. It is conductance. I am saying resistance reciprocal is conductance. That SI unit should be ohm inverse. Ohm inverse is given one special name in SI system, Siemann. S-I-E-M-A-N-N, Siemann. Simply capital S is the symbol people use while writing symbolically. And I should tell you one more thing. When you are talking about electrical resistance in a circuit, people use this symbol. I am making use of, please see one spiked line this way. And the spiked line on either side has connectors. Left side connector is there, right side connector is there. Altogether the whole thing is known as resistance circuit symbol. I hope we have seen all these things with which we are well acquainted with at high school level. But still we are supposed to have that much basic in mind to pursue our present study. But anyhow, of course, to be frank, under very short answer questions and in our textbook, all this information was given in a nutshell. Then let me hope that you have written something. We'll go for the next part now. So far what I said is, we talked about Ohm's law, and let me hope that you remember the statement of Ohm's law. And with the help of Ohm's law, we have written this much: V is equal to R into I, and the SI unit of R happens to be ohm. But let me tell you one more thing. Just now I said R can be written as rho L by A. Na? Let me replace that R with rho L by A into I. The minute I go for writing like this, your brain must be telling one more thing. Why can't you rewrite this formula in this fashion? V by L, please see, by cross multiplication you'll get back the same thing again. Rho I by A, am I right? Same thing I have rewritten. This is nothing but current flowing per unit area. Current per unit area, I by A. This quantity in physics is given one special name, current density. As we have seen already in electrostatics, what is that V by L? It is potential difference per unit length. Potential difference per unit length or potential gradient, is it not going to be the uniform electric field magnitude? So capital E magnitude is equal to rho. Just now I was telling you I by A is known as current density J. Forget about its direction, all that. Think about magnitude. That is why I am putting modulus on either side. Then what should be the SI unit of that current density J? I. It is ampere, area meter square. So shall I say that ampere meter power minus 2 happens to be the SI unit of this current density? Now, this current density J is equal to J into rho is equal to E. Let me rewrite in this fashion. J modulus is equal to E modulus divided by, because you may wonder why you are writing modulus all the time, because electric field is a vector quantity, it has a direction. You may wonder why he is not writing unit. So forget about its direction part, concentrate only on the value magnitude part. This divided by rho. But just now I was telling you the reciprocal of this rho, specific resistance, is specific conductance. Or if you think that rho is nothing but resistivity, resistivity reciprocal should be conductivity sigma. So shall I go for writing like this, please? Sigma E modulus. Remember, this is the popular formula in which you are interested. Many times you will be making use of this. Mod J is equal to sigma mod E. This is also the outcome of Ohm's law. Then I want to tell you a little bit more. Just, go for catching up with one thing. Wherever there is a chance, please go for noting down few things so that you will first remember what has happened now. Then later, I'll give you the notes also. Happily, you can read all these ideas in an orderly way. But don't forget to make some note of your own. Then, something else. Under Ohm's law, we said just now, I have written something, hope you remember. What I have written just now? I was writing this much, V is equal to R, no, R, I, okay. But instead of R, we started substituting rho L by A, na? Rho L by A into I, and I have written this much. This rho I by A is nothing but J, right? And this V, this L we transfer to the LHS. V by L we called it as E. Of course, if you want, you can write this as J is equal to sigma E also. That's fine. This is something that is over just now. Then I want to tell you something else. Why electrons are moving in a conductor? Because they are experiencing some electric field. Let me show one conductor with this much big cross-sectional area, easy to understand. I am showing this as a cylindrical part. A conductor has cylindrical cross-sectional area in general. Let us say the cross-sectional area of the cylinder is L, and let me say that delta T is a small time interval for which electron traveled. Then, strictly speaking, according to your knowledge of electrostatics, when charge Q is subjected to electric field E, capital E, what is the force acting on it? It should be QE. Am I right? F is equal to QE. Then we know pretty well, there we have solved one problem also, if you remember, that F is MA, MA is equal to QE. Then what is the value of A equal to? It should be QE divided by M. So a charged particle having charge Q, when subjected to electric field E, if it has a mass M, it gets accelerated. It experiences QE by M acceleration. But let us not forget one more thing. After all, when you apply electric field in any region, positively charged particle travels in the direction of electric field, whereas negatively charged particle travels exactly in the opposite direction. Now, in our lesson, the concentration is on moving and mobile electrons constituting electric current. So, I should say like this. If electric field is in this fashion, if this is the direction of electric field is a vector, it has some direction. Then electron, which we call as E minus symbolically, gets accelerated opposite to that. So let me say that the acceleration experienced by an electron is equal to minus, instead of Q, because the magnitude of charge is E, I will write like this, E by M. I will repeat, whenever charged particle is subjected to electric field, it experiences acceleration in the direction of electric field, provided it is a positive charge. But now we are talking about an electron which is negatively charged. So undoubtedly, electron also experiences acceleration, but in the opposite direction to the electric field. Because charge of the electron is E, I replaced Q with E and I have written the formula like this. Now, to be frank, we are talking in electricity, the terms of mechanics. I hope you remember what you have studied under kinematics. Under kinematics, you would have studied one formula in the last year, V is equal to U plus AT. The final velocity acquired by a body with initial velocity U, traveling with acceleration A over a time interval t is given by V is equal to U plus AT. If you make use of this idea, in the present situation, what should be the final velocity of an electron? Here, matter of one more convenience. A material has so many electrons. A electron, B electron, C electron. Let us start giving names. Then, in general, we talk about ith electron. The final velocity of ith electron will be initial velocity of the ith electron minus E by M into T. After all, I am making use of V is equal to U plus AT. I am writing this conclusion. This is the final velocity after time interval T. Then we should say one more thing here. Once if you say after time interval T, it gets this much velocity. The next question, an accelerating electron, because it is traveling in a material, there are so many doors, so many hindrances, so many difficulties, walls coming in its way. It will be dashing with those walls, it will be coming back. So whenever that is happening, the time taken by an electron to experience one collision will be something. Actually, all electrons traveling in different directions will not experience same amount of difficulty. Some may be traveling a bit briskly, some may be coming back in the opposite direction after hitting. Here, the lesson you have studied in the name of collisions of 11th class should also be entering your brain. This way, when electrons are hitting the wall, again when they are coming back, when they are taking some time, each electron takes its own characteristic time to come back in one direction. Then it was found that when such a thing is happening, the average time interval taken by electron to come back after a collision, people call it as relaxation time tau. Please observe, we introduce one more new term, relaxation time. It is the time taken by an electron to hit one crystal lattice and to come back. And this time is not saying, that is why I should say the t value small t I have written here in the name of ith particle. Maybe slightly it may be more than tau, that is relaxation time. It may be less than tau, but in general, the tau happens to be the average value, right? Then we go for writing one more thing. If somebody asks you the question, what is the final velocity of an electron if it takes tau time? For that, let me write not Vi. I am writing one general equation. Capital V is equal to Ui. Ui means average initial velocity of all particles involved in the given sample in the form of metallic wire. And it was found that as these electrons initially will be moving in different directions in a haphazard way, people say that initial velocity is 0. So initial average velocity is 0 for all electrons minus this EE by M into tau. Remember, I am using that symbol tau to talk about relaxation time. That is the average time taken by an electron to come back or to go in a new path after experiencing some collision. The minute you write this, your brain must be telling one thing. Finally, even though the electron is experiencing acceleration, we came across one formula where we are saying that V is equal to minus E by m into tau. As you see here, all these values are constants, which clearly means that an electron, even though it is experiencing electric field, it travels in different directions. Ultimately, it travels with some fixed velocity in a specific direction. The name given to that fixed velocity in a specific direction, people call as a drift velocity. VD, my dears, observe we are coining a new word. Drift velocity. What is the drift velocity? It is the average velocity acquired by all electrons while traveling through a material, and moreover, it is independent of something, time. In general, this value t you are taking as relaxation time, it is the average time, but you don't think that one velocity will be moving at 4 meters per second, other will be moving at 5 meters per second. As a whole, all electrons move with some constant velocity, which you are calling as a drift velocity. Remember, and if I go for showing you one conductor like this, if electric field is in this direction, electrons exactly will be traveling in the opposite direction. I hope I told you already, if this happens to be the drift velocity opposing the electric field, this is the direction in which electrons are traveling. But people say electric current is exactly opposite to that. I told you long time back, this direction people call as conventional current. That is maybe our forefathers' way of thinking, which we are continuing now. This is the direction of conventional current because electrons are traveling in this direction. Electron current is towards left side, whereas conventional current is towards right side. So shall I conclude like this? Electric field direction and conventional electric current direction are same. These two are the same now. Only the electron current direction will be opposite to this. With this knowledge, we will go for something else. Don't worry, I know. First it appears to be slowly confusing, then slowly it becomes clear, provided you make a note of what you are hearing now, and if you supplement that with your notebook. Still, if you have some more doubts, you can clarify later also. Then let us go for the next part. Let me show you one conductor. This is one conductor. It is a cross-sectional area of the conductor, which you are treating in the form of a cylinder. One minute. Controls. I feel like just redrawing this much. Then we started believing one idea now. The drift velocity of the charged particle or electron is Vd. Don't forget the very basic definition of velocity. It is the displacement in unit time, in 1 second time. If you think that the time interval under consideration is delta t, what is the distance traveled by the electron in delta t? Just you multiply that Vd with delta t. I am thinking that Vd into delta t is the small displacement experienced by the electron. And let me say that the cross-sectional area of this conductor is A. And I say that the charge, again, I'm sorry, it happened as it happens now and then in a class. We exceeded our 11:15 time. Shall I stop now? Shall we wait till we go for the next class? All right. because the viewer number, just it came down by one and again it is changing. It means somebody is planning to stop. Okay, it's all right. Anyhow, bear this much in brain. We'll meet again in the next class. Thank you very much.